Let's discuss today the Fermat Principle. What is Fermat Principle? I write down that statement first. See, the ray of light traveling from one point to another by any number of reflection or refraction follow that particular path for which the time taken is least. I'll give one more statement for this similar statement of Fermat Principle, that is same, that will describe the length is minimum. So I write another statement, same statement written in other words. So in other words, I can write this as, in more general form, a ray of light traveling from one point to another by any number of reflections and refractions follow a path for which, compared with all other neighboring paths, the time taken is either a minimum, maximum or stationary. This is the Fermat Principle stated by Fermat in 1658. Right? It says a ray of light traveling from one point to another by any number of reflection or refraction follow a path for which, compared with all other neighboring paths, the time taken is either minimum, maximum or stationary. That can happen only when the path traveled by the path light is extreme. Right? I'll make use of this Fermat Principle and prove the law of reflection and refraction. Right? So let's first prove the law of reflection using Fermat Principle. We have two laws of reflection. One is the incident light, normal and reflected light lie in the same plane. I write it down. The incident light. The second is the incident angle is equal to reflected angle, or the angle of incidence is equal to angle of reflection. The angle of incidence equal to angle of reflection. Now you can have these two laws from the Fermat Principle itself. Suppose we have an interface between the two medium. This plane is the interface between two medium. And suppose we have a point A over here and point B over here. See, this is whiteboard in this plane, white plane. Suppose this is the plane interface between two medium. You have this another medium, this is one medium, this is air, this is glass, say. Right? Then a light is falling, light can fall, light can take this route. So the light can take any route, right? It can be, say, so the light can fall like this. Light can also take this route. Light can also fall like this. Right? Out of all these, and see, this is the normal. Say normal here is, this is normal. In this case, this will be the normal. I do it by different color. This can be the normal. In this case, say this is normal, right? Normal. So you can visualize yourself that the path for which the incident light, reflected light and the normal lie in one plane will be a least path. Incident light, say this is the path for which the incident light, reflected light and normal lie in one plane, then you can understand that this length from here to here, this will be greater than this. Suppose this one is AOB. Suppose AOB is the path. AO is the incident light and OB is the reflected light, and this is normal. If they are three in one plane, then compared to this path, this is going to be higher. This length A to O dash, obviously AO dash will be more than AO and O dash B will be more than OB. So compared to all the path which involve the incident light, reflected light and normal in one plane is going to be the least path. Now in one plane also there can be several possibilities. Let me draw this. In one plane also, this is the plane, it is the interface. Suppose this is the point A and this is the point P. And suppose light propagate from A to B involving one reflection at the interface. So there can be several paths, several possible paths. I'll draw 2-3 paths. These are the possible paths. We have drawn 3 paths. Now let's see which is the possible path, which is as per the Fermat principle. Say this is, suppose I use the variable x to characterize different paths. Suppose x is the variable characterizing different path, right? This is angle of incidence. Suppose x is the variable by which different paths are characterized. Say this is distance d. Now let's find the value of x or condition on x so that the time taken is minimum. Time taken is minimum only when the path is minimum, the length of path is minimum. So this is, suppose for this path, this is x. So this will be t minus x. So what can be the length of path? This is O, right? Or let me write over here. So the length of path is going to be AO plus OB, or AO is, say this is distance A and this is distance B. So AO is A square plus x square, whereas OB is B square minus D square x square. So for path to be minimum, your dl by dx must be 0, or dl by dx is x upon a square x square d minus x upon b square is 0, or we can write x square x upon equals to d minus x square, or this can be simply written as, if suppose this is theta I and this is theta r, then this will also be theta I and this will be theta r. So I can write x upon a square x square, this is a square x square is AO, that's equal to sine theta I, and this is sine theta r, or I can write theta I equals to theta r, theta is theta r. So light will take a path for which the angle of incidence equals to angle of reflection. Now I'll use Fermat principle to prove the law of refraction. I'll first write down the law of refraction. This is the law of refraction. The incident light, normal and refracted light lie in the same plane. See, I can prove this in the same way as I discussed for law of reflection. The second one is angle of incidence and angle of refraction follows Snell's law. What is Snell's law? mu1 sine theta I equals to mu2 sine theta r. Suppose we draw an interface over here. So this is the interface, right? And suppose light starts from point A and it has to move to, say, point P. So it has to move to point P, and let's suppose it takes the route. The path taken by it is, say this can be the path taken by it, right? This is the path taken by it. I'll draw the normal. Normal is going to be, this is going to be the normal. Now I have to prove that this angle theta I, angle of reflection, and this is the angle of refraction, follow the Snell's law. So this is medium mu1, this is medium mu2, and let's suppose this is A and this is B, distance is B. and let's suppose this is x and the whole length this is d, so this will be d minus x. So the optical path is going to be, since the medium are different, we have to consider optical path. Optical path, this is O suppose, so optical path is mu1 into AO, and AO is a square plus x square, and OB is in the medium mu2, so mu2 into b square plus d minus x whole square, right? So x will be such that the length is minimum as per the Fermat principle, so dl by dx is 0, and dl is mu1 into x upon, this is a square x square, and mu2 into d minus x, and this is b square d minus x square, so that's equal to 0. So it is mu1 sin theta I equals to mu2 sin theta r.